So yes, as he said, I am working in Université, and I'm working in a cryptography team here in Versailles. But what I really do is to study computer algebra. So what I like, in fact, is in life is to make algebraic operations on a computer and see how well and how fast this works. Okay, but a very classic and important application of that is cryptography, so the science of secrets. And so that's why I'm going to talk to you about that today. So this lecture is an introduction really to the subject of cryptography. It's not at all exhaustive, so there are a lot of things that I will not talk about today, but we will see that even with quite simple mathematics, we can actually do some interesting things in cryptography, and I will show you how to do so today. Okay, so let's jump in. And the first thing that I will talk about today is cryptography. So what is this, and what is the point of cryptography? So it's a very ancient field. So it comes from the Greek, the word cryptography, and it means secret and hidden. So it's the first part of the word, sorry, crypto, that means secret. And the last part, graphy, means to write. Okay, and often you will see cryptology also next to cryptography. So the cryptology is the science of secret. So often those two words are expressing the same idea. So if we look at the meaning of the word, we see that what we want to do is to write secret things. Okay, and so the cryptology will be the study of secret codes. Okay, so there is math behind that, a lot of math actually. So I will show you just a little of that today. So that's why we're going to study the mathematics of secrets. But first, let's see what's the goal of cryptography and the applications. So the very basic, the first role of cryptography will be to enable two people that are usually, it's a tradition called Alice and Bob, because the letters are A and B. So they want to communicate. And for whatever reason, they do not want anyone else to be able to hear the communication or to read the communication or to copy the communication. They do not want their communication to be public or to be understood by everyone else. So usually the third person is called Eve, because she's eavesdropping. So she is listening to the conversation. Okay. And yeah, so they want to be able to send a message to each other or a whole conversation, and they do not want to be spied. Okay, so as I said, there are a lot of reasons for which they could want that. Okay, for example, if Alice and Bob are two people working in the military, maybe the informations that they want to send, sorry, are classified. Maybe they are very important, there is a battle coming up, and it's very important not to let the enemy know about that. So in fact, the military communications were probably the first one to want efficient cryptography. And so it was important back in the Greek time and the Roman time. So for example, Julius Caesar was already using cryptography, so both for military purposes and also for sending letters to his family. So I'm not sure what he was talking privately with his family, but he didn't want that to be public, and that's his right. So he was using cryptography. And well, today too, I'm sure that military people still use cryptography, and even in the Second World War, there was this famous machine, the Enigma machine, that I will not present today, sadly, but it's quite interesting. So the Enigma machine was used to encipher, so encrypt all the conversations of the German during the Second World War. And a lot of efforts were put into trying to decipher, to break this machine. Okay, so there's even a movie about that that you might have seen, that is called I don't remember, but okay, it's okay, I will remember it during the lecture maybe. Okay, so you might also want to pay something on the internet, and in that case, you don't want your banking information public. So in that case, also your communications will be encrypted. So in that case, you are maybe Alice and Bob is a computer. So it's the server that will have your banking information. But yes, if you want to go to an HTTPS website, so as Antoine Chamberlois said at the end of the previous lecture, you will have cryptographic protocols in that case also, and some of them, yes, are based on elliptic curves. Okay, and of course, encrypted messaging apps such as WhatsApp or Telegram are also using cryptography. So in fact, really, if you speak to someone through a digital communication channel, you are surely using cryptography, even if you don't really know it. So it's really everywhere. Okay, so I talked about Julius Caesar cipher. So it was the protocol, the cryptographic protocol that he was using to send letters to his family. So in that case, the idea is quite simple. It will be to shift all the letters in the message by some constant number k. So for example, if k is equal to 3, you will have A that is transformed into D, you will have B that is transformed into E, C into F, and so on. And when you are at the end of the alphabet, you just go to the beginning. So in fact, Z is transformed into C with that model. So as an example, let's see how to transform this sentence with the Caesar cipher with k equal to 3. So first, you just bring the letters all together without spaces, and then you will just shift all the letters. And so we see that with this quite simple idea, you can already make some message totally unreadable. Okay, so well, except if you are really really good at languages, you can maybe recognize something here, but I am not myself able to recognize any message here. And so this new message, LQMXVW and so on, can now be sent to someone. And if I am Eve, I am an enemy, a spy, an adversary, we often say, I will not be able to deduce anything from the message because I just don't know what this message means. Okay? So, but now, so yeah, a quick drawing of the situation. So what we did was just to shift these letters by 3 units, and you can shift them by more than 3 units if you want. And a simple way to decode the message is to look at this drawing. Okay, but okay. But as I said, if someone wants to be able to decrypt the message, they have to share a secret, what we also call a key, because if I receive this message, L, Q, M, X, and so on, and if my friend who sent me the message did not tell me what was the key, well, in that case, I do not know anything more than a spy, or than someone who could have intercepted the message. So I cannot do anything. Okay, so I, in fact, really need this information here, k equal to 3. Okay. Okay, so this thing stays, but I will delete it. Okay, so in fact, in what we call symmetric cryptography, both participants must share a secret. Okay, they must share a key before beginning to communicate. Okay, and in fact, this secret will be used by the one sending the message to encrypt the message. Then we have an encrypted message, so we are happy about that. Okay. And on the other hand of the communication, Bob wants to decrypt the message, and he also needs to use the secret, to use the key to decrypt this message. Okay. And so, as I said, in Caesar cipher, the key is that number k. Okay. If you know k, you can decrypt easily, but if you do not know k, that can be quite hard. Okay, so that's what I wrote just here. So if you know k, well, you know that to go from this encrypted message to the original message, you just have to shift back by 3 units the letters. And so L becomes now I, Q becomes N, and so on, and you are able to recover the original message. So, okay, that's good. And if you do not know the key, well, in that case, it's really harder, okay? Because if you do not know the key, you have to try all the keys. And so if you have a short message, such as the one that I put in this slide, you would try the key k equal to 1, that gives you nothing. You try the k number 2, that gives you nothing, so you're unhappy both times. And well, you can go on, and for that example, with k equal to 17, you find that the message was, this one should not be so easy. Okay, and now you're happy. So it seems that on one hand, if you have the key, you're happy. If you do not have the key, you're unhappy. but still you can try to make things work and you can try to recover the key. Well, so this works here because it's a small example, and so we are using a very small number of keys. But in real life cryptography, the number of key is really huge. And so you cannot at all find all the keys yourself. You cannot find all the keys even with a computer. And even with all the computers on the planet, you could not find the keys, because they are just too much. The cryptographic protocols are designed to have many keys so that you cannot just try to recover the key by searching through all of them. So that's off the table. And usually, if you want to break a crypto system, you will have to understand deeply how it works, and you cannot just hope to find the key at random. Okay, so now that I have presented to you some facts about cryptography and our goal, I will introduce, well, maybe you know a lot of the mathematics that I will talk about, but I will give you some mathematics that will be used to define first really interesting and modern cryptographic protocol. Okay, so back a bit to Kaiser cipher. We said that we have letters and we shift them in some direction to encrypt the communication, and you shift in the other direction to decrypt the communication. Well, in fact, instead of representing that with a circle and with some letters, you can use mathematics to represent this crypto system. Okay, and how do we do that? Well, we will just say that A equals to 0, B equals to 1, and so on, up to Z that is equal to 25. And in that case, the encryption operation will just be the addition with the constant K, and the decryption operation will be the subtraction by K. Okay, so it's really a simple idea. You just replace letters by numbers. Because we like numbers, we can do operation with them, and so they are easier to manipulate. But now there's something that is quite odd about that. It's that when you are shifting Z that is equal to 25 by, let's say, K equal to 1, then you should have A equal to 0, right? Because I said that when you are at the end of the alphabet, you just go back to the beginning. So we would really like to have 25 plus 1 equal to 0 and not to 26. Well, the problem with usual integers is that they do not have an end. So you can never go back to the beginning. But well, even if integers do not have an end, we could say in a sense that modular integers do have an end. So what we would like to create is some kind of structure like that is a circle, and when you are at 25 and you add 1, you obtain 0 instead of obtaining 1. Instead of obtaining 26, sorry. So the first numbers are the same as usual. After 1, you get 2, and then 3, and then 4, and so on. But when you're at the end, and when you're at 25, the next number on your list is still 0 because you're on a circle like that. Okay? And we can define such numbers properly. This is called Z over 26Z. Sometimes It's also denoted as Z with 26 as an index. And these kind of sets of number will prove to be very useful in cryptographic application. Okay, so let's go back on some things that I'm sure you already know quite well, in fact. So if I have two integers A and B, we can say that A divides B when there exists a third integer C, such that B is equal to A times C. Okay, and we note that by A with the middle bar B, and so we have that 3 divides 12 because 12 is equals to 3 times 4, but it also works with negative integers, so -2 divides 6, and it also works with 0. So there are no numbers that divide 0, but 0 divides any number. Okay, so for example, we have that 0 divides 42 because 42 is equal to 42 times 0. Okay, well, that's just a convention. So here, in fact, we could here it's as if I have replaced these numbers by letters, and I work with the alphabet like that. So after A there is Z and so on. But we could also say that A is 1, B is 2, C is 3, and that's not really really important here. It's just that we have to start by something, so we start by 0 and 8. But yeah, really doesn't matter too much. Yeah, that's a bit too soon maybe to answer that question. I will have more examples at the end of the talk, yes, and I don't want to spoil you. Okay, so I was on the other slide, and I just realized that I wrote something quite horrible, because that's really the opposite. That's 42 that divides 0 here. Okay, and yeah, and not the opposite. And it's because 0 is equal to 42 times 0. But I'm sure you also that, so that's okay. Okay, so this is the divisibility definition. Okay, and now there is another thing that will be very useful for us. It's the Euclidean division. Okay, because what is not too nice about the divisibility is that with integers, it does not always make sense, because for example, in Z you cannot divide 5 by 3, for example, because 3 does not divide 5. But you can always make Euclidean divisions, okay, and they are defined that way. So, and I guess you might have already done it when you were a kid, because we, well, when I was a kid, I studied those kind of divisions at school when I was like before 10 years old. Okay, so if you have two integers A and B in Z, with B that is more than 1, you can always find an integer Q and an integer R, such that A is equal to B times Q plus R, and with the condition that R is strictly less than B. So that's an important one, otherwise it could not be unique. And so the integer Q is called the quotient of the Euclidean division, and R is called the remainder. Okay, and so we also write A equals R mod B to say that R is the remainder of the Euclidean division of A by B. Sorry. So let's look at some examples. So, for example, 17 is equal to 5 times 3 plus 2. And so in that case, we would say that 17 is equal to 2 mod 5. Okay? We have 39 that is equal to 14 times 2 plus 11. So 39 is equals to 11 modulo 14. Okay? So what it means really is that if you consider that 14 is equal to 0, well, in that case, you have 39 that is equal to 11. And finally, so if you look at 18 modulo 3, it gives you 0. And that is because, in fact, 3 divides 18. Okay, it's 8 times 6. Okay, so so before I go back to that, so it gives you a way to define things like that, because here we want to consider that 26 is equal to 0. So what we are going to study are the operations that are done modulo 26. Okay, so each time we have 26, we will consider that it's 0, and that allows us to put an end to the integers, if we want to say it like that. That's not really rigid. Okay, so a bit more definitions before we go back to cryptography. So if we have two integers a and b, we say that a is congruent to b modulo n if we have a equal b modulo n. Okay, and the integer n is called the modulus of the congruence. And we have a lot of nice properties. So if we have a equal b, it means that in fact that n divides a minus b. And you have all the nice properties that you could want. So the congruence work well with the addition, with the multiplication, and with the equal signs. So if you have a that is equal to b modulo n and b that is equal to c, you will also have a equal to c. So in fact, since all these operations work so well, we can define something that is called the equivalence class of an integer. So it will be the set, so it's not one number, it's a whole set of all the integers that are congruent to a modulo n. Okay, and then what we will denote by z over nz of the integers modulo n, so that we that we write z over nz, or also sometimes z of n. Okay, and so it's the set of equivalence classes of integers 0, 1 up to n minus 1. So it's a convention that we usually take the same sign for the number and its set and its equivalence class, but those are two different objects. So you have to keep in mind that that's not exactly the same. And you can notice that it's not the same because in some cases you will have that 25 plus 1 is equal to 26, and in the other one you will have that 25 plus 1 is equal to 0. So if you work modulo 26. Okay, and so in that set of numbers, so there are no more integers, but there are other kind of numbers. You have all the operations that are performed modulo n. And so for example, in Z over 3Z, you have that 2 plus 2 is 4, but 4 is equal to 1 in that space, in that set. So you can write, that's not an error, that 2 plus 2 is equal to 1. And you have a lot of other strange things that can happen. So for example, Z over 6Z, in Z over 6Z, sorry, you can have that 2 times 3 is equal to 0, okay? Because in that set, you have that 6 is equal to 0. Okay, so now that we have that, as I said, we can just, instead of representing the letters by the actual numbers in Z, we will represent them by elements in Z over 26Z. And so now the encryption is really done by addition by K, and decryption is really done by subtraction by K. And so if we want to represent that, so here there are the red points, now the black points are the numbers in Z over 26Z. So if you add 1 to 0, you obtain 1, then you obtain 2, then you obtain 3, and so on. And two numbers that are linked to each other are just the image of the encryption by the Caesar cipher with K is equal to 3, or the image of the decryption. It depends on which way you're going. Okay? And so, in the end, thanks to mathematics, we have described a very ancient crypto system, quite strongly, as I would say. So we have designed a way to express this crypto system. So of course there are more complex crypto systems, and in a few slides I will present to you a crypto system that was invented not so long ago, but we need just a bit more of tools to do that. So in Z over NZ, some elements are called invertible. So they are called like that when you can, so an element X in Z over NZ is called invertible when you can find an element Y such that X times Y is equal to 1, okay? So if you think about it, it's really the same notion that you know for real numbers, for example, because in the reals, you have that a number multiplied by its inverse is equal to 1. So here, that's really the same idea, but just in another kind of set. So yeah, so if you have in the real number, sorry, why doesn't it work? Okay, so if you work in the real numbers, for example, if you have 1 divided by 3 multiplied by 3, you get 1 by definition, okay? And that's because 1 divided by 3 is the inverse of 3, okay, in the real numbers. But this does not make sense every time. So for the elements in Z over NZ, not all elements possess an inverse, okay? So that's why they have a name, and that's why it's a special property to be invertible in Z over NZ, okay? So the inverse of X is usually denoted by X to the power -1, and the set of invertible elements of Z over NZ is denoted by Z over NZ with a little cross, okay? And so, as I said, not all elements are in this set, as we will just see now. So let's take another example of what we call a modular ring, in fact, a Z over 10Z. So let's take, for example, 3 times 7. So it's 21, okay? But since we work modulo 10, and since 21 is equal to 10 times 2 plus 1, we have that 3 by 7 is equal to 1, okay? In that spatial space. And so we have exactly found the property that we were seeking. We have 2 elements such that their product is equal to 1. Okay, and in that case, so we can write that the inverse of 3 is 7. And that's the same in the other direction. So we also have that the inverse of 7 is 3. And in fact, you can try to make all the products by hand if you want, and you would notice that the elements that are invertible in Z over 10Z are just 4, and there is 1, 3, 7, and 9. And in fact, both 1 and 9 are their own inverse. So 1 times 1 is equal to 1. So it's its own inverse. And 9 times 9 is equal to 81, so it's 1 again. You can be your own inverse in Z over NZ, it's no big deal. Well, it was already the case with the real numbers, because you have 1 times 1 that is equal to 1, and also minus 1 times minus 1 that is equal to 1. Okay, but here it's quite the same, in fact, because the 1 here plays the role of 1, but the 9 plays the role of minus 1. Okay, because 9 is 10 minus 1, in fact. So there's a logic behind it. Okay, so we can study these particular elements. Oh, sorry, I have to go back to normal mode. Okay, so you can study the structure of the invertible elements, and sometimes this is called a cyclic group. So because it can be generated by only one element. Okay, so by the powers of one element that is invertible. And this element is in that case called the generator. And in fact, the invertible elements in Z over 10Z was an example of a cyclic group, because, as I said, there are only 4 elements, and these elements are generated by the powers of 3. So if you take 3 power 0, you have 1. So that's by definition, in fact, that's cheating a bit. But you have that 3 power 1 is equal to 3, 3 power 2 is equal to 9, and then 3 power 3 is equal to 27. That is 7 in Z over 10Z. And then you can also check that 3 to the power of 4 is equal to 81, so it's equal to 1 again. And then it's just a loop. You would go through the values 1, 3, 9, 7, 1, 3, 9, 7, and so on. So that's a loop, that's a cycle. So that's why it's called a cyclic group. Okay. Well, there is another notion behind the group terminology, but I will not go into it today, even if it's really interesting. Okay. So we can represent this always by a nice drawing. So here, in fact, in red, you have the numbers in Z over 10Z, and in blue, you have numbers in that are invertible in Z over 10Z, and that form a cyclic group. And so they are all generated by multiplying by 3. Like if you have 1, you multiply it by 3, you get 3. Then you multiply it by 3, you get 9. Then you multiply it by 3, you get 7. And then by multiplying by 3 again, you have 1. Okay? And some last results before going to one very interesting cryptographic protocol. If you have a number x in z over nz, you can immediately know if it's invertible, in fact. So you don't have to check all the products by hand. You just have to compute the GCD, so the greatest common divisor of x and n. Okay. So I did not recall what the GCD was, but it's the biggest number that divides both x and n. Okay, so for example, 3 is in z over 10z. We already saw that, but we can check that this is true because the GCD of 3 and 10 is equal to 1. Okay, because the divisors of 10 are 2 and 5, and the divisors of 3 are just 3. So they are and 1 is always a divisor. So in fact, in that case, the biggest divisor of both 3 and 10 is 1. And that's the same for 7 and 32. Okay, in 32, the only prime divisor is 2, and in 7, the only prime divisor is 7. So their GCD is equal to 1. We also say that they are coprime or relatively prime. I will use this terminology in the future. And we also know, so that's a complicated results, in fact, that the set of invertible elements of z over nz is a cyclic group if n is equal to 1, 2, 4, if it's a prime power, or if it's 2 times a prime power. And this theorem will be helpful right now because we will talk about a crypto system that use the fact that the invertible elements are in a cyclic group. Okay, so let's jump in cryptography again for a bit. Well, until the end of the talk, actually. So what we have seen until now is that you can use symmetric cryptography, such as Caesar's cipher, and it will bring you some interesting way to encrypt your communication. Okay, that's all right. But the huge drawback is that both Alice and Bob have to know the secret key. And it's this secret key that will allow to encrypt and to decrypt. So whoever you are, Alice or Bob, you have to know the key. But then, so the problem is no more how to exchange a message in a secure way. It's how to exchange the key prior to the communication. And so, well, there are solutions to that. We could say that they could meet in person and just write down on some paper the secret key and then use it. But that's not always possible. So if Alice and Bob just live very, very far away, that's just not possible. Right now with the pandemic, that argument is even stronger. It's not always possible to travel, but that's not the only way in which it's not always possible. So if Alice and Bob are 2 persons, yes, they could meet. But if Alice is a credit card and Bob is an ATM that wants to know if the credit card is a real one, then they cannot just discuss and and make a key because they're not thinking, right? And that's the same if just one person is a computer and the other one is a person. You cannot just talk with the computer and say, okay, let's use this key. So we have to find another way to exchange a key before being able to communicate. And okay, and for that, we could say, okay, so let's send a key, but with a communication channel, whatever the communication channel we have. But in that case, if the communication channel we use is not secure, well, then everybody can read the key that you are exchanging. And then in that case, it doesn't make sense because everyone knows the secret key, and so anyone can decrypt your messages. So at that point, you should be wondering, well, are we doomed? Can we do something about it? And there is a solution, very elegant, that was found not too long ago. So in fact, in the 70s, by Whitfield Diffie and Martin Hellman. So who are those two gentlemen here, and who published a very famous article now that is called New Directions in Cryptography. And they proposed a solution for managing the key exchange without revealing any data, so anything about the key. So what's the magic behind that? So how can we do that? So to do their exchange with the Diffie-Hellman protocol, which is the name of their protocol, they will agree on some public information. So that's information that everyone can know, okay? You can share this information with your neighbors. It doesn't matter because it's the operation that you will do later that will be important, okay? So you find a prime number P and you find a generator G, okay? The generator G of Z over P times Z. So there is always such a generator because, as I said in this theorem here, in the case where n is equal to p, it's a cyclic group. Okay, so that's why we talked about that. That's simple mathematics, but it's helpful here. Okay, then when you have this public information, you will choose integers, but that you will keep secret. Okay, so Alice will choose a number a that is between 2 and p minus 2. So she cannot choose 1 or p minus 1 for obvious reasons that I will discuss later. And Bob does exactly the same. So he chooses a number b that is between 2 and p minus 2. And then that's where the magic happens. Alice will compute G power little a, and Bob will compute G power b. Then they send their computation to each other. So Alice that have received the number b will compute b to the power a. So it gives G to the power b to the power a, which is G power a and b, a times b. And Bob does the same, so he computes a times b, and it gives G power a times b. So here it works because b times a is exactly the same as a times b, okay, for integers. So if you work with other objects in mathematics, it's not always true, but here this is true. And now, in fact, they share a secret because they share what a number that they are the only one to know, that is a G power a and b. So let's sum up the situation on a drawing, okay? So let's use, for example, P equal to 23 and G equal to 5. Okay, so you you could do the computation by hand if you want. That's not too big numbers to do that. So let's say that Alice chooses A equal to 4 and Bob chooses B equal to 3. Okay, so the blue elements here are public, so that's why P and G are in blue, and the secret elements are in red. Okay, so A equal to 4 is Alice's secret, and Bob's secret is B equals to 3. Okay, so now, as I said, Alice will compute G to the power A, so G power 4, that gives you 4. And Bob will compute, on the other hand, G power B, so it's 5 power 3, and that gives him 10. And then he sends it to Alice. And now, both individually, they will compute, so 10 power 4 and 4 power 3. And you can check that will always work, but it gives you 18. Yeah, it gives you 18 in both cases. And now you have a secret key. So I can, in part, answer the question about the numbers of the key, or the spaces in which the keys are. But let's say here, if you take P that is a prime that is very, very big, like maybe hundreds of digits. Okay, so we know how to generate primes like that. It's not even very long. So you take a prime that has many, many digits, like 100 or 200 digits, and then you perform this operation, and now you have a secret with your friend Bob or your friend Alice. That is a number that can be very big, because that's a number that can be between 1 and P minus 1. So you have a lot of possibilities for the key, and then you can use this very big number to use it as a key that you will use in other crypto systems. So that's what I wanted to say, actually, is that, okay, before that, okay, no, so before bringing to the security, just let's say something fast. Here, now that you have a secret, you will use this secret for another crypto system. So for example, another symmetric crypto system that enables a lot of keys. Okay, so there are a lot of symmetric algorithms. The one that we use today, in fact, you can check, you can look it up on the internet. It's called A, E, and S for Advanced Encryption Standard. And with that algorithm, you can use keys. You can use 2 to the power, so it should be 2, 5, 6 keys. Okay. So in that case, you really have a lot of keys, because I think that, well, that numbers has 2056 bits, and in digits I don't know how much it is exactly, but it should be more than 100 also. So it's really a lot of keys. And so this, the Diffie-Hellman protocol, enables you to find a key and to agree on a key. And when you have agreed on a key, you're just really happy, because now you can use symmetric cryptography with your friend and communicate without being listened to anyone. Okay, so, but yeah, another very important question is that thing even secure? So if someone is able to listen to our exchanges with Alice and Bob? Well, is that adversary, so Eve, able to find the secrets of Alice and Bob? So if we look at it, what an adversary is able to listen to here is this number A, this number B, because they're all in blue, and also G. Well, P also, but P is really to make the computations. It's not that important. So the adversary knows G, A, and B, and what he wants to find is this little secret here, A, and this little B here. Because if he has little a or little b, he can just do the same computations as Alice or Bob and find the secret S. Okay. So what we have to make sure is that even given some informations, so here the informations are G power A and G power B, nobody can find the value S that is equal to G power A times B. Okay, and that in fact is known as the discrete logarithm problem. Okay, why is it called discrete logarithm? It's because when you have a power like that, G power A, finding this little a is called the logarithm with the real numbers. But here you're working with discrete sets of numbers, so not continuous sets. So it's called the discrete logarithm. Okay, and in fact, it is really hard to recover x from just the data of G and G power x. There has been extensive research on it. It's still active, in fact. So there are still articles about that from time to time, in not really in Z over NZ, but in other kind of sets. And we do not really know any efficient technique to solve the discrete logarithm. Well, except in some rare cases that we just know how to avoid. And when I say that we do not know any efficient technique, what I mean is that with a computer, we do not know any algorithm, so any recipe to find x when we have G and G to the power of x. So yeah, that's why we believe that Diffie and Hellman protocol is secure, is that we do not know any way of doing it, even if we have been searching for more than 50 years. So that sounds hard. But we could say, okay, can't we just guess what the value x is? Well, if you have P that is equal to 23, yes, sure, you can do it by hand. You compute G power 1, G power 2, G power 3, and so on and so on. And it's not too hard because G was 5 in that case. And you can, yeah, in this small example, find x without any problem. Sure. But now, if you take P that is equal to approximately 100, in that case, okay, you take some G and some G power x, it should be quite difficult to do it by hand now. So you could still do it. I'm not saying that you can't, but it would take you a very long time. Whereas with my computer, I did it yesterday, and it took me, I think, 3 milliseconds, something like that, just by looking at all the values without thinking too much. So it was really fast. But then again, it's not because a computer can do it in a few milliseconds in a small example that he will be able to do it with big examples. So if you take p that is around 1 million, then the computer takes 0.5 seconds, sorry. And if p is around 1 billion, it takes 9 minutes. And so I've said that the p that we would look at are really big. So the biggest p that I wrote here as 10 digits, I guess, because it's more than a billion. So it takes 9 minutes for 10 digits. But now imagine if you take p that is 100 of digits, then in that case, even a supercomputer cannot do it, and probably even all the computers on the planet working together cannot do it in a reasonable time. Yeah, so the best algorithm that we know to do that generically, so when we are not in any particular cases, is has an exponential complexity in okay. So if I will write something. Okay, it works. So if you have, let's say, n elements. Okay, no, it doesn't work too well. If you have n elements, the best algorithm that we know has complexity square root of n. So we say that it's exponential in n, because in fact we look at the logarithmic size of n, we look at its number of bits. That's why, well, in fact, that's a very bad complexity. What we would like is a linear algorithm, so something that takes maybe, I don't know, 2 times the logarithm of n, because that's, I hope it's readable, because I have issues with my pen and I'm not able to do it unless with the mouse. So yeah, here it's an algorithm that yeah, that is exponential, and its name baby step, giant steps. That's a very yeah, that's a very classic technique, in fact, in algorithmic, the baby step, giant step technique, and it's quite smart, but that's the best you can do, and that's not smart enough, because still, if n has, I don't know, 100 of digits, then its square root will have will have let's say 50 digits, and it's just too much, because it means that, yeah, you can just double the size of n and you would have the same complexity as doing it without any idea, without any algorithm, with just looking one by one all the elements. So, and by doubling the size, I mean that you use twice as much digits, not 2 times n, because what we really looking at is the number of digits that you have, because it's what tells you the size of the number. So yeah, the baby step, giant step algorithm is smart, but not enough in the general case. And then there are a lot of other algorithms when you are in a special case. And also, so in some cases we have techniques that break this. So it means that finding the discrete logarithm is not hard, but in the general case, all we know is the baby step, giant step technique, and that's why in real life cryptography, on purpose we use examples where we do not know any additional techniques. And these, for example, the one that Antoine Chamberlain was mentioning before with the elliptic curves, we do not know how to do the discrete logarithm with a better technique. So we have to use that square root complexity. Yeah, absolutely. So that's something that I did not mention, but that's a very good question. Here, when I say that something is hard or something is easy, I mean it with a classical computer. Okay, so the algorithms that I talked about, like the baby step, giant step technique, is with a classical computer. And in the case of a quantum one, this is in fact way easier. So in that case, you have to use what are called post-quantum crypto systems. And while this is very fun and interesting, I will not talk about it today because it involves mathematics that are a bit more complicated. But yeah, it totally makes sense. And yeah, the discrete logarithm is broken, we say, in with quantum computers. Sorry. So yeah, very good question. So okay, it is secure on a classical computer at least, and we could discuss if quantum computers are a threat, but maybe later. So what we can do with the Diffie-Hellman algorithm is that now we can use symmetric cryptography because we have a common secret key thanks to the Diffie-Hellman exchange. And so now that we have a key, we can just use our favorite symmetric algorithm. And so we were able to exchange our key on a public communication channel. So that's what is important here. And even if anyone can listen to the information that we exchanged, nobody is able to recover the key, except if they have a quantum computer that is big enough, which is not the case actually right now. But everyone is trying to build one. Okay. So there's another thing that I want to talk about that is really elegant in my opinion, and it's asymmetric cryptography. Okay, so we have seen that the Diffie and Hellman exchange protocol is quite nice because it enables to use symmetric cryptography. But in some sense, we have also seen that Alice and Bob still have exactly the same rule. So they both choose a random element and they compute some powers, and then they exchange the computations, and then they compute their secret. Okay? But in fact, we can do even better than that. We can encrypt messages without even the need to exchange a secret key. So until now, I've always said that you need a secret key to encrypt messages, but that's not entirely true because we will see that we can make things such that it works without the need of a secret key. And yeah, so right now you should wonder how this is possible. Is it black magic or something like that? Well, in fact, no. That's just a great idea again by some mathematicians. So in asymmetric cryptography, the roles of Alice and Bob will not be the same, and there will be two kinds of keys: private keys from on one hand, and public keys on the other. And so public keys will be used to encrypt the messages, and private keys will be used to decrypt the communications and the messages. Okay, so in that case, let's say that Alice is the one that will create a pair of keys, a private one and a public one. And if Alice has a pair of keys, only Bob will be able to send message to Alice, and Alice will not be able to send messages to Bob. That's why this is no longer symmetric. And in that case, in fact, she will use her so Bob, if he wants to send a message to Alice, will use her public key to encrypt the message, and then Alice will use her private key to decrypt the message. So let's sum up that again. So first, Alice creates a pair of keys, a public key and a private key. Okay, and then Bob, who has a message to encrypt, will encrypt it using the private key. So now there's an encrypted message that can be sent on the internet, or on any other communication channel. And then Alice, that has the private key, can decrypt the message. And since only Alice knows the private key, only Alice will be able to decrypt this encrypted message. Okay, so this is the sketch of the ideas, but now we have to actually propose a solution to have something like that. Okay, and I need some more theorems to do that. So I'll go a bit faster maybe for that part, because I want to introduce you the protocol. So there is a function named Euler's tangent function that counts the integers that are up to n and that are co-prime with n. So meaning that it will count the numbers x such that the greatest common divisor of x and n is equal to 1. Okay, so we can try some examples. We would see that phi of 10 is equal to 4. You can just check all the greatest common divisors and see that there are only 4 values for which it's 1. Phi of 7 is equal to 6, and phi of 35 is equal to 24. So for those 2 values, you can also check all the all the numbers one by one and check that it's 6 and 24. But in fact, we can do better than that, because we have propositions that tell you some things. So first, what I wanted to say is that phi of n exactly is the number of elements that you have in Z over NZ cross or star. Okay, because we have said that the elements that are invertible are exactly the ones that are co-prime with the modulus n. And so since phi exactly counts the number of elements that are co-prime, it exactly counts the number that are invertible in Z over NZ. Okay, so that's good to know. That's a way of defining this function. And it is also multiplicative, meaning that if 2 integers x and y are co-prime, then phi of x times y will be phi of x times phi of y. And that's why, in fact, we can compute phi of 35 in a faster way, just by saying, okay, this is phi of 5 times phi of 7, and this is 4 times 6. Okay. Okay, so there are some famous theorems using these. First, the Fermat's little theorem that says that if you have p and x, so p a prime number and x a positive integer, that is coprime with p, then you have that x power p minus 1 is equal to 1 modulo p. Okay, so that's a famous theorem. You don't really need to know about Euler's Gaussian function to state it. But then there is Euler's theorem that is a direct generalization of Fermat's Leibler theorem, because it says that if x and n are coprime positive integers, then we have that x to the power of phi of n is equal to 1 modulo n again. And that's a generalization because that's a proposition. Phi of p is always equal to p minus 1. And that's because every number that is below p will be coprime with p. So there is p minus 1 number that are like that. Okay? And so now that I have these theorems, I can introduce to you the very, very famous protocol of Rivest, Shamir, and Alman, which will enable us to use asymmetric encryption. So it means that we will be able to encrypt messages without having to share a private key. Okay, and so it's really used even today. Even when you go on the internet, a lot of protocols just use the RSA crypto system, even if it's quite old because it was invented just 1 year after the Diffie-Hellman protocol, so almost 50 years ago. And so the idea here will be to work in a modular space again, so with the modular integers z over nz, and with n that is the product of two primes. Okay, so in that case we have that phi of n is equal to p minus 1 times q minus 1, and okay, that's it. And then Alice again will choose an integer e that is coprime with that value p minus 1 times q minus 1, and will publish the key that is e and n. Okay, so the value n is public, and the value e that she chose is public too. Okay, so fair enough. And then what will remain secret is the exact value of phi of n and an integer d such that e times d is equal to 1 modulo phi of n. So that d, I will not talk too much how to find it, but there's an algorithm, in fact, that is called the extended GCD algorithm that gives you exactly that. And okay, and so d and phi of n is the private key. Okay, so now how do we encrypt data and how do we decrypt data? So for encryption, remember I said that we would be using the public key. Okay, and so now what we will do is to start with a message x, and the encryption will be just x to the power of e modulo n. So we can always do that because we know n and we know e. Okay, and then on the other part, the decryption part will be that we will send an encrypted message y to y power d modulo n. And now you cannot do that if you are not Alice, because you do not know d. Okay, so you have to know d to encrypt the message, to decrypt the message, sorry. Okay, now there is a quite easy result, in fact. It's that the RSA crypto system works. And so for any message x that is in z over nz, we have that d of e of x. So if you encrypt the message and then you decrypt it, you will find the message that you had in the beginning. So it's the same as saying that x to the power e times d is equal to x modulo n. And why is that? Well, in fact, we just have to use Euler's theorem, because we have that x to the power of phi of n is equal to 1. That's the theorem. And now we also know that E times D is equal to 1 modulo phi of n. And so this really means that phi of n divides ED minus 1. And so another way of writing that is to say that E times D is equal to 1 plus K times phi of n. And so x power E times D is only x power 1 plus K times phi of n. And so it's only x in the end. And so you have recovered the message that you had in the beginning. And so now a small example of how does that work. So first, let's say that Bob wants to send to Alice some message. Okay, and so first Alice will choose two integers. So here I chose 3 and 5. She will compute phi of n. So here it's 8. She will choose E that is coprime with 8 here. So 3 is okay. And she will publish 3 and 15. Now Bob just has to compute his message 7 to the power 3, and it gives him 13 modulo 15. Okay. And now Alice, that has also her secret key D. So here, because it's a small example, we also have D that is equal to 3. But for the sake of the example, we will say that it's okay. It's never the case with big examples. So she will compute 13 to the power 3, and she gets back the 7 that Bob sent in the beginning. And so even if we take numbers that are a bit bigger, we have things that are all different, and in that case it makes more sense, but it's hard to check that all these numbers really work. But that's also a good way of noticing that in real life we absolutely need a computer, of course, to do that, okay? Because all these results and all these operations are with quite big numbers, so it's not possible without a computer. Okay, and so, well, in that case, the modulus n that we are using in real life has thousands of digits. So it's not hundreds, but 1,000 this time. It's really big. Okay, so again, is it secure? Can we break this crypto system? And why haven't we been able to since 50 years? So in fact, the best technique that we know to break the RSA crypto system is to find the factorization that is secret of n. And that might sound a bit easy to do because we know how to make a multiplication. So we should probably know how to make a factorization. But in fact, no, that's really hard. And we do not know any very efficient algorithm for factorization, even today. Even if it's simple on paper to understand what is factorization, it's still an active domain of research to find an efficient algorithm to do that. And there are still teams of researchers that are trying to break some records and to factorize a big number. Okay, but why is it the best technique that we know? It's because if we know P and Q, then we can recover phi of n, that is secret. And if we have phi of n, we can recover D. Okay? So as I said, we believe that factorization is really hard in practice, or at least large P and Q, and that's why we believe that RSA is still secure even today, and that's why we use it so much. Okay, but there are in fact a lot of open questions. First, we do not really know if factorization is the best way to break the RSA crypto system. That's the best way that we know, but it doesn't mean that's the best way at all. Maybe someone even knows how to break RSA but didn't tell anyone. And if it's the case, he would be probably very rich at the moment. And even we do not know if factorization is really hard. What we know is that we are not able to do it in a very efficient manner. But once again, maybe there exists an algorithm somewhere that is able to factorize integers that are big in an efficient way, and it's just that we do not know it. And since you brought up quantum computers are able to factorize big numbers, but so on paper, in fact, we have a quantum algorithm that is able to break the factorization in an efficient way. But with the actual quantum computers, I believe that the best that we could do was to factorize 15 or maybe 21. I'm not sure about that. I should check, but it's not really able to do anything that we didn't know for now. Okay, so I'll just go pretty fast on these last ideas. But if we take a step back, what we have defined is a function that we call one way, meaning that in one way it's easy to compute, and in the other way it's supposed to be really hard. So for example, if we look at z over 17z and we look at 3 power x, the function that maps x to 3 power x, we see that it's easy to go from x to phi of x, but if you look at the table, it's not really appealing what could be a simple recipe to find x with f of x. So it really means that in one way it's simple to compute, but in the other way we do not really know how to do it. Okay, and so that's what was used. That's what was used in the discrete logarithm problem. And there is another thing that is called the trapdoor one-way function, and in that case it's really the same. So it's a one-way function, but that with an additional property becomes easy to compute in every direction. And so that is the example of the RSA encryption function, because in that case, if you know the factorization of the modulus n, you are able to compute x power e, but you are also able to find x when you have x power e. So what we want, in fact, in cryptography, so still today, is to find one-way functions and trapdoor one-way functions. And we have seen that, so those two kinds of functions are the basis for asymmetric cryptography. And we do, in fact, that's still unknown if they are truly one-way functions, because we're not really able to prove that a problem is difficult, or we're not able to prove that we cannot do better than what we already know now. And these, in fact, what is interesting in my opinion is that modular arithmetic, so the operation in z over nz, brings a very easy algebraic structure, but it also gives challenging problems on a computer. So it gives difficult problems that we are not able to solve efficiently. And when we do not know how to do something efficiently, well, it's sad, but at the same time, it's really useful in cryptography. So there are still a lot of open questions in cryptography, especially, well, in cryptography, but also in asymmetric cryptography. And a lot of people are working on it every day, trying to make sure that when you pay for some shoes on the internet, your code is not stolen by anyone. So okay, I think that's a good time to finish. And yeah, no, something I just wanted to ask also that I did not cover everything in cryptography. Yeah, in fact, I covered just a very small part because I wanted to have an introduction of asymmetric crypto, but there is a lot more to discover with other mathematical objects. And yeah, so elliptic curves, as we already said, but also systems of equations, finite fields that are interesting also, and so on. Well, I think, yeah, yes, Bosco, yeah. Yeah, in that case, it would prove that, well, so there is, yeah, I think that in that case, yes, it would prove that there exists a fast algorithm, but still the problem is the same because even with the P equal NP problem, even if you know that there is an efficient algorithm, then you have to find it. And that may be the very difficult part in many problems. That even if you know that there is a simple solution, it can be very hard to find. And so even if you have some elegant proof that there exists an algorithm, well, you still have a lot of work to do because you have to write it down and to find it yourself. So yeah, that would, I guess, say that there's a problem, but that's not a real issue because we just don't know how to do it, even if we do know that there's a solution. I'm not too sure about that one, but yeah, it's yeah, honestly, I'm not too sure about that one, and well, so for the cryptography as a whole, that's sure that it would not affect everything because there are still things in cryptography that are not related to primes. So even if that's a substantial part of cryptography, there are still things that are not based on that. So it would not break down everything. But on the other hand, those crypto systems that are based on finite fields, no, I couldn't tell. Maybe I would tell you something wrong. So, but that doesn't scare me too much because yeah, there is a big part of cryptography that is not at all related to primes, and even if the RSA crypto system is, we are changing the algorithm that we use. So yeah, and in fact, the recommendation of the security agencies right now is to not use RSA anymore because of the quantum computer more than because of the Riemann hypothesis. But so yeah, in fact, we are scared a bit, but more about the fact that a quantum computer could exist than that we could have a solution to the Riemann hypothesis. Yes, it would, because if x and n are not coprime, then it means that you have found a prime factor of n, because n just, okay, that I can write somewhere maybe. So yeah, it would be a big problem, but in that case, in that case, you really have a problem. So we know that n is equal to the product of two primes, right? And so if you take at random some x such that the GCD of x and of n is not 1, then it's probably equal to p or to q, because that's the only two possibilities. So in that case, it means that you have recovered some prime factor, and in that case, it breaks everything. But that's a case that never happens because the probabilities are very, very, very low. But yeah, it would be a problem. Okay, yeah. So it's because so that's an interesting question. Okay, you're right in saying that n is public, and then we could just ask ourselves, so why can't we just compute phi of n, right? We know phi, we know its definition, and maybe we could just try on a computer or try it by hand. But the problem is that in the definition of phi, to compute it, it's better to know the factorization. And in fact, you can prove that knowing phi of n and knowing p and q is the same thing. So it's equivalent. That's one of the that's advertising for the problem station, because that's one of the problems that are in the problem sheets. But yeah, that's in fact that's the same thing to know phi of n and to know p of q, because it's not so easy. You cannot just compute phi of n. That's computationally difficult. So that's difficult to compute, even with a computer. Very interesting question. So a book that I really like is called it's Handbook of Applied Cryptography. It's called Handbook of Applied Cryptography. It's a book by Meneses and two co-authors that I do not remember. I can look it up. Let me 2 seconds. Okay, I cannot see my slides anymore, but that's okay. Okay. So yeah, it's called Handbook of Applied Cryptography, and it's a book by Meneses, Oshut, and Van Stone. And it's a really nice book because it begins with the basic. So really, what I talked about today, and it's really easy to read. And then it also really goes into the details of what you can do with cryptography. So it's really nice. It's a big book, but very classic. Everyone loves it, apparently, me included. And well, the careers are there are a lot of things you can do. You can be a researcher, of course, if you want. But in fact, a lot of companies are hiring cryptographers to make sure that the thing that they're selling is secure in some way. So, for example, if you sell, I don't know, well, if you sell credit cards, you have to make sure that your credit cards are secure. But that's there are a lot of examples where you want to sell a product with cryptography in it, since it's everywhere. You could be a spy also, but I just don't really know how to become one. So, but yeah, there are a lot of things you can do with a degree in computer science and in cryptography. Right now, the things that are used to make cryptography work, so the tools that are being used, are more based on mathematics than physics. So maybe one day someone will find a crypto system that is based on some physics property. That's not impossible, but right now it's usually more based on mathematics, like in subjects like number theory, or yeah, usually number theory, in fact. But if one day there is a new crypto system that uses physics, in that case, yes, it would be the development in physics would bring some new insights on cryptography. But right now, it would be the developments in mathematics, and especially in number theory, that would bring new ideas in cryptography. So first there is so one of the answer may not satisfy you, but there is a historical reason. So the RSA crypto system was, in fact, the first public key crypto system to work for encryption, and you can also use it for many things. It's in fact quite amazing how one single idea can make so much things work. So, for example, the digital signatures can also work with the RSA crypto system. And so, since the RSA protocol was here the first, and since it does so many things, people got really used to it, and it was used everywhere, and it was implemented everywhere. So that's one part of the answer. Another part is that yes, it's quite easy, very easy to understand, quite easy to implement in a secure way. So that's very popular, because why would we want to use something complicated when we have something simple? But now, well, in fact, since 2000, something like that, well, not me, but the security agencies have been beginning to say that RSA should not be used so much anymore, because we have many other things that are maybe a bit more complicated, but either more efficient or more secure. Well, secure is not the way, but let's say they're more efficient, because you can use things that are smaller, because they are more security proofs. So in the end, it's more efficient. And these things are elliptic curves, for example. So we have very good cryptographic protocols using elliptic curves. And so 10 years ago or 20 years ago, the security agencies, so the one in the United States, the NIST, which is the one that is the most listened to, began to say that we should use elliptic curves everywhere, because that's just more efficient. But so yeah, that's RSA is not the best in every domain, but still, because it's so simple and because it was there in the first place, it was there very soon, it's still widely used. But that's not a good reason why, right? For now, we don't have any computer that could do that, but that's what we call the quantum threat. So even if it's not possible right now, it could be in, I don't know, maybe 50 years. I'm not saying that it's 100% probability that we have a quantum computer one day, in fact, because it seems physically very difficult to build one. So I don't know if we will ever have one. Well, at least one that is big enough or strong enough. But so for now, the answer is no, we cannot do that. Not to the point of it being interesting in cryptography anyway. But usually what we think in cryptography is that Let's imagine that you have some classified information that you want to keep secret, and so you encrypt it, and then you send it to someone, and so no one will be able to read it today, but someone could copy it, put it on his computer in his garage, anywhere you want, and maybe in 50 years, when we do have personal quantum computer at home, maybe that person will be able to read what you wrote. So that can be thought like that, and maybe you can say, okay, if I write something right now, there is no way that it will be important in 50 years. Maybe not for you, but for, I don't know, states or very big companies, it could be important to hide information for a very, very long time. So that's why even now, even if we do not have quantum computers, we are working on algorithms that are post-quantum, so that are able to resist any quantum computer, even a large one and a strong one. Okay, so yeah, I do not know these definitions by heart. I think that a pseudo prime should be a number that is composite and that fails a criminality test, the one of Fermat, I think. So what I will say is that when you want to prove that a number is prime, you have algorithms that are probabilistic, so that they will tell you that the prime that you are studying is prime, but it's not really sure. So it's sure with probability 99.9999%, but it's not sure. And you also have algorithms that give you the answer, and it's not probabilistic, so it's really sure. And when it says yes, it's prime, it's definitely prime. And when it says no, it's not prime, it's definitely not prime. But the problem with these algorithms is that the ones that are not probabilistic are very slow. Okay, so in fact, it's there is an algorithm that is supposed to be quite fast because the complexity is not so bad. It's look, it's a polynomial complexity, but its implementation is quite hard, and we do not know how to make it work with very big primes. And in particular, we do not know how to make it work with primes that are involved in the RSA protocol. So for the RSA protocol, we have to use the probabilistic algorithms. And sometimes you have some numbers that resist the test, meaning that the test will tell you that they are prime, when in fact they are not prime, they are just composite numbers. So some of these numbers, some of these numbers are called pseudo-prime because they are supposed to be primes, but in fact they are not. So they are composite numbers. So a famous family of such numbers is Carmichael numbers, and they are very famous because they resist the they resist Fermat's test of primality.